Okay. In 6.8 RSG, we're looking at a ready of determining if a given value or point is a solution to an equation. So what they're going to do is give us a value or a point and then ask us if that's a solution. So if we have this equation and we want to know if x equals -5 is a solution, the easiest thing to do is just plug in x equals -5. So every time we see an x, plug in -5. So if we do that, it looks like this, where you can see -5 has been replaced, or has replaced the x. Then you simplify it and you get -6 equals the square root of -16 plus 2. Well, -16, square root of -16 is an imaginary number. That gives us 4i plus 2. So we can't say that 4i plus 2 is the same as -6. So therefore, -5 is not a solution. Another way to look at this problem is to solve it and see if -5 is the answer we get. So we could subtract 2 from each side. That gives us -8 equals square root of x minus 11. Then we could square both sides, giving us 64 equals x minus 11, because squaring something square rooted cancels out the square root. Then we could add 11 to both sides, and that gives us 75, which is not -5, so therefore x equals -5 is not a solution. It also happens to be an extraneous solution. If you check it, this is not possible, as we would see in the graph, because the other way that we could figure out if x equals -5 is a solution is we could graph x equals -5 and the two sides of the equation and see if x equals -5 is indeed a solution. In red, you can see the square root of x minus 11 plus 2. In blue, you can see y equals -6, so the other side of the equation. You can see they do not intersect in the graph, which is why 75 is an extraneous solution. And then you can see in green that x equals -5 is only intersecting with -6 and not with the other graph, and so therefore it's not a solution to the problem. Then we're going to be given a point and an equation and asked to determine if the point is a solution. So this time we have two variables that we have to plug in, an x and a y. So we're going to plug in our x to the x value, so 20 goes in where the x is, and 5 to our y value, so 5 goes and replaces the y. And then we just solve just like we did to see if each side is the same. So I get 5 equals the square root of 9 plus 2, and so 5 equals 3 plus 2, and so therefore I can say yes, 20, 5 is a solution to this problem because 5 equals 5 once I plug them in. The other way I could look at this is if I graph it. So I can graph both the equation and the point and see if the point does fall on the graph. And if you look here, the point is indeed on the line that's drawn, so therefore 25 is a solution. Then in the set, we are going to solve square root and inverse variation equations. So instead of there being a number on one side and a equation on the other, an expression on the other, we have two expressions equal to each other. One way to do this is to graph it and see what the intersection is, just like we were doing back in 6.6. So Jasmine's method was to do just that. She plugged in both sides to Desmos, or her graphing calculator, and saw where they intersected, and that was her solution. So the solution is x equals -2 because the intersection is at -2, 2. But then, as you saw in your class, Kevin had a different method. He wanted to solve the equation for x. So what he did was he took this equation, he wanted to get rid of that square root, so he squared both sides. He then expanded that work into x plus 4 times x plus 4, because that's what it means to be squared, and created a quadratic equation out of it. Well, it was already a quadratic, but he expanded it into standard form of the quadratic so that he could set both sides equal to 0 and factor. So he gets x squared plus 8x plus 16 equals x plus 6, subtracts x and 6 from both sides so that he can get it equal to 0, since that's how we have to solve for quadratic functions. X squared plus 7x plus 10 equals 0 gives us a factorable equation of x plus 2 times x plus 5. And so then we can find what makes each factor equal to 0. X plus 2 equals 0 and x plus 5 equals 0. So x equals negative 2 and x equals negative 5. So those are our two solutions to the problem. Well, we have to make sure that there are no extraneous solutions, so we're going to check it. So we're going to plug in negative 2 to our original equation. We find that negative 2 plus 4 is 2, and the square root of negative 2 plus 6 is the square root of 4, and that gives us 2 equals 2. So that is indeed a solution. And we plug in negative 5 and find that negative 1 is equal to the square root of 1, and that is not a solution because negative 1 is not equal to positive 1. So that's extraneous, which is why in Jasmine's method, they only found one solution of x equals negative 2 because Kevin's second solution is extraneous. Francisco's method does all the same things Kevin's method does, but when it gets the equation equal to 0, he simply graphs it and finds where the graph hits 0, which is at negative 5, 0 and negative 2, 0, just like in Kevin's method. Then he checks it and finds exactly what Kevin found, that negative 2 is a solution and negative 5 is an extraneous solution. So the answer is x equals negative 2. Then we can do it with inverse variation equations. So if we do it Jasmine's way, we're just going to graph the two sides of the equation, x plus 4 equals y, and y equals 6 divided by x, and see where they intersect, which are at these two decimal answers. Or if we do it Kevin's method, we will multiply both sides by x to get it out of the denominator. Then we will find that we can get a standard quadratic equation, and that is by setting it equal to 0 by moving the 6 over. And then we find that we can't factor it, so we have a couple options. One is we could convert to vertex form by completing the square. So that means that we're going to divide this b value by 2. 4 divided by 2 gives us the 2 that you see here in the equation. Oops. Oh no. And then we have to get back to negative 6. So when we do x plus 2 squared, we get 4, and so we will subtract 10 from that in order to get back to negative 6. And then once we've completed the square, we can add 10 to both sides, take the square root of both sides, move the 2 over, and get negative 2 plus or minus the square root of 10. Square root of 10 cannot be simplified, so if we want to see what the decimal answers are that are similar to Miss Jasmine's answers, we will plug this in the calculator. But negative 2 plus or minus the square root of 10 is a more precise answer. The other option is to solve using the quadratic formula. So that is negative b plus or minus the square root of b squared minus 4ac all over 2a. And we plug in our numbers to that. So we plug in negative 4 to the negative b plus or minus the square root of 4 squared minus 4 times 1 times negative 6 divided by 2. Then we simply simplify, giving us the square root of 16 plus 24 under the radical. And that gives us negative 4 plus or minus the square root of 40 divided by 2. And then that can be simplified to negative 4 plus or minus 2 times the square root of 10, all divided by 2, because 4 times 10 gives us 40, and the square root of 4 is 2. And then that gives us -2 plus or minus the square root of 10, which is exactly what we got in the other answer. Or we can look at Francisco's method, which is where we use Kevin's method all the way to get the quadratic equation equal to 0, and then type it into our graphing calculator and solve for the zeros. Kevin's method is the only way to get the most precise answer of -2 plus or minus the square root of 10, but the other two methods find us an estimated answer. And then you can check for extraneous solutions by plugging in our solutions to our x values. And we see that indeed they are solutions to our problem because they equal the same thing on both sides. Finally, we have the go, where we're solving problems involving direct and inverse variation relationships. In this case, hot chocolate sales vary inversely with temperature, and stores sells 45 hot chocolates when it's 72 degrees outside. We want to know how many hot chocolates they sell when it's 30 degrees outside. If it's varying inversely, we can use our inverse variation equation of y equals k over x, where k is a constant. And so we can put in our variables, hot chocolate sales equals k over temperature. Then we plug in our numbers that they gave us. We know we sell 45 hot chocolates when the temperature is 72 degrees. Solve for k. Get this number for k, which again is a constant. So our equation is hot chocolate sales, oh, that is a misspelling. Hot chocolate sales equals 3240 over temperature. So therefore, hot chocolate sales are going to be 3240 over 30 degrees. And so we know that we sell 108 hot chocolates on that day when it's that cold. Then if we look at ice cream sales, we can do the same thing, but this time it's varying directly with temperature. So we're going to use our direct variation equation, y equals kx. Ice cream sales equals k times temperature, plugging in our variables. And then we plug in our numbers, 45 equals k times 72, and solve for k, which gives us a 0.625 or 45 over 72. And so we can plug that back into our equation for k, and then plug in our new degree 30 and find that they sell 18.75 ice creams, which means 18 ice creams, since you can't sell 0.75 of an ice cream.